is okay. One is high performance computing, as HPC we can call from now on. And this HPC, we use computers and supercomputers as a power of compute something for us. But we need, maybe depends on our scientific project, we need more RAM, more CPU, more GPU, storages, connections, task management, schedulers, depends on how many people using those things in a server or in a pipeline and so on. And we know supercomputers nowadays, they're huge computers, and they are in supercomputing centers, and many countries have those kind of supercomputing centers, and they are now racing with each others to be the most powerful computers that they have. And we need tools or programming languages or architectures to use those kind of big facilities. And we need some programs or some good algorithms to run all our projects, all our scientific goals for them. And we have some examples in real world. I can give some of them. And in science, what we are why we are using HPC, in particular in astronomy, like simulations, data imaging, data storage, and so on. And there are two very important examples for us. One is SDSS, one is another one in the future, and is still going on, LSSD project. And the other one, the other powerful tool nowadays, it's very popular. We are trying to understand, basically, when I attend another workshop in machine learning in AI, machine learning in astronomy, people are still debating about which machine learning algorithm we will use, which kind of features we need, how we manage all those data. We can see inside what is going on, or we don't necessarily, it's not necessary. I don't know. Yeah, we all debating on those kinds of topics in machine learning, still ongoing. In machine learning, we use supervised and unsupervised methods. So I'm going to explain all those, and algorithms that are already written as a libraries or frameworks in different programming language for different programming languages, and so on. And basically, we classify or clustering in our to our data with using this machine learning. And we need tools, environments. Maybe I can give a quick example at the end. We are going to do in we are going to do my example in Anaconda by using Jupyter Notebook, and we choose the Python, or you can choose R, or you can choose any other programming languages for doing machine learning. And at the end, maybe we can be an statistics scientist, data mining people, or data scientists. So most of astronomers, after their PhD, they choose another way to go on this data science projects, not astronomy, but the others also. If you know those kind of tools, you can do anything in the world besides astronomy. So maybe you can be a data scientist at the end. Let's start with the first powerful tools. Our first powerful tool is high performance computing. High performance computing, basically, there are many computers in a very big room. There are all compute nodes, so you can use each of them with a master node. So you can connect that master node, and you can run your code, you can run your project in master nodes, and if you have a chance to have whole computing center, it needs more than millions of cores. So you can divide your job to those cores. So it means you will have a very big power, the core power of computers, just like that. And then maybe you need not the cores, but also the RAM power, because the very fundamental things of the computers is we should be able to communicate with the RAM, our RAM, random access memory, and the CPU. This is the very necessary, very big problem, because nowadays the main problem is to reach the RAM as soon as possible. Okay, the technologies allow us to do that, but we run everything. Whenever you push a button on keyboard, your let's say character goes directly to RAM. Okay, and then your CPU is trying to calculate, trying to run, trying to understand that RAM part to what is going on there. So if you run a program, it goes directly to the RAM, and you need to run it as fast as you can, besides the other program working on the in the computer. And those kinds of high performance computing centers, they give just you a RAM and CPU power, and also storages, and the communication very fast communication systems, just like InfiniBand technologies. So you can run your code without any other disruptions. So we need to pass that part. And if we consider, there is also the GPUs. It's a graphical processor unit. It is basically it's a video card. So you can use their powers. They have much more than there are many cores, much more than CPUs, if you compare with the GPU and CPU, but less frequency speed. So those kind of things we consider. Maybe you should not consider, but if we do those kinds of science, if we need to use those kind of things, we should be aware of those kind of technologies. If you want to do HPC, you need maybe you need a MPI, message passing interface. So your program can talk with the other nodes, or one node can talk another node. So you can at the end you can collect all your data if you give many cores. At the end, you can use OpenMP in one single machine with many cores. Like, let's say if I have a 8 cores computer, if you can use OpenMP, you can directly use your 8 cores for your program, something like that. So many low-level programming languages like C, Fortran, and so on, maybe you need more to use those kind of things rather than using Python, because Python doesn't go directly to the core of the programming process, but C goes there. And you need more processors, CPUs, RAM, if you consider those kind of big centers. And problems, you need core speed, you don't need latencies, you need more storages, very big amount of storages, and all those are very expensive. At the end, for energy, if we consider energy, it's not efficient for us. So those kind of technologies is too much cost for big countries also. There's a example, computer center. It is actually already changed the name, not Python. It was before Jaguar, now it's Python, and now already changed to another name. As you see on the right bottom picture, it's how is big if you compare with a man. It's how it's a very big computer facility, just like that. And it has 500,000 cores before, and the power, as you see. You can follow those kind of things from top500.org webpage. And if we can see today's computers, where are they on the list? And this is a very competitive list, because all big countries racing in here to be the first or to get inside the top 10 supercomputers. So recently, Japan gets the first top of the list, supercomputer Fukuoka supercomputer with 7,600,000 cores, and it is very fast computer, supercomputer. And as you see, the second one is Tamit. It was first before, maybe half year ago, it was first. So America, United States was the first one. And as you see, there's the fourth one is China. But this is so frequently changing. And I think the new Cold War, before it was for space race, now it is for supercomputing race, but not between in Japan and others, in between United States and China is all we face today in other areas or fields also. Okay, just in case you can maybe later on you're interested. What we do in science with this high performance computing, we can do experiments without doing it real or trying it in a real room or in a very big laboratory. First, we do all things inside the computers. We simulate things. As you see, there's a picture of a rocket. You can change the wings of rockets, the same rocket with the same fuel amount of fuel. It can goes to maybe more distance if you change a little bit warp to it is wings at the end. So those kind of things you can test inside the high performance computing centers. No, but how we can do the fluid dynamics to do that, as you see on the middle. There's a picture in the middle. You see the coming fluids and how it's shaped on the rocket. And we simulate the universe on the right part of the picture. We simulate the universe. So how the dark matter we see in the universe as we have from a simulation. And so those kind of things we can do with HPCs. And some HPCs have different type of usage, like IBM Watson, still running, it's a running project, and it is still on in the web. So you can use that Watson computer. It has no hard drive. It has just RAM. So this computer is super fast by using only RAM. Everything we know as a knowledge from the web pages, from the Britannica Encyclopedia and so on, we put inside that computer, that Watson computer, and it can easily calculate everything very fast because it directly uses the RAM and CPUs in between. So we put Western computer in a competition. So maybe Jeopardy competition. This is very interesting because the answer supposed to be a question. If let's say there's an example, if we ask like that, Frank Sinatra is one of the very popular singer. So you should answer like, who is Frank Sinatra? So this computer can easily understand who, which, why, when, those kind of questions, just like a human being can do. How about in astronomy? How we use those kind of things, those kind of supercomputer centers or supercomputing power? Just below the HPC in astronomy writing, there is played pictures. So 20 years ago, we more or less we were just considering some stars on that picture. One or two we consider we were interested in. But nowadays, with the very big surveys, we have many pictures with many filters of pictures. In many filters, we take data, we observe the universe, we observe the sky, different parts, several times. So we have very big amount of data. At the same time, we use a grid technology. We call grid technology. So if you have a computer at your home and its configuration is different than someone else, so everybody has their own configuration, but the same data directly goes to your configuration, and without you, it can run in your computer, and it can run someone else's computer. So the data is determined or analyzed in different configuration computers. We call this grid in all over the world. So we use those kind of computers, the whole world supercomputing system, just like that. It was using for SETI project before. So also we have the power. We have I as a detector or as a tool to classify things. So we did a Galaxy Zoo project to classify galaxies, galaxies' properties, and so on. So those kind of things give us another opportunities to understand the galaxy structures or morphology. So we know if we see the galaxy, this is the spiral, this is the elliptical galaxies, and we catalog those, we label those galaxies. And then today's machine learning algorithms can easily use those labeled data, and what we have at the end, I will show you a small example about that. And then we take those kind of pictures on the right side. We determine their magnitudes, their distance. We keep their picture, small cutout images. We trying to find is there a cluster or some density areas and so on. So we trying to do science with many of objects at the same time simultaneously. So astronomical data needs HPC at the end, because with this amount of data, so we need programming for data, programming languages, efficiently programming for data. We need pipelines to do that as an automated way. We need to archive data. Anytime we can reach there again, we can download, we can use those kind of data. We should use, yeah. And then managing data, where we will put it, where we store the data, and how long we will put data in there, and so on. And we need scientific results. So analyzing those kind of data, how we can do that. In the near future, we will have more data comparing with the 20 years before. So we need more. We will have more data, and we will do more analysis. And then simulating maybe data and doing some statistics on that data and graphing and showing and comparing those kind of data. And at the end, it's a full of very complicated processes. As you all know, I guess, large synoptic survey telescope, the LSST, is going to be operational close soon, and it is the biggest. It has the biggest camera, to 3.2 gigabyte CCD, and it will have 15 terabytes per night, and it's going to be public instantly. So it's going to be very huge for astronomers to manage those kind of data. Okay, they already do some pipeline, prepare some programs and so on. This is a dynamic process, dynamic project. So how we can reach those kind of data? Let's consider like that. If you consider, if you're working on galaxies, you can have millions of galaxies in a current survey. But with LSST in 5 years, after LSST in 5 years, it's a billion of one in the very depth of the universe. So it means you should put all other galaxies taken from LSST in your code, in your project, in your scientific goals. Otherwise, they are already there. Galaxy data will already be there. And as you know, the Gaia is already working on the stars, and it's per day 40 gigabyte data it collects, and so on. Till now, SDSS also has terabytes of data, and also the dark energy survey to calculate, to analyze, and to store the whole data from the telescope works in La Serena and send all data to NCSA to United States. It's a fiber cable way to have the data, to put the data to the United States and so on. So we need those kind of things there. Okay, so today's data astronomy point of view, we should have those kind of tools to manipulate and manage to do some scientific researches at the end. And the second powerful tools is machine learning. We can separate machine learning very easy ways: supervised learning and unsupervised learning. What are they? If we have on the bottom, there is a supervised learning graph, how we do that. As an input, we have apples, and we know they are apples, and we say to the machine learning algorithm, they are apples, and the machine learning algorithm creates a model create a model with those kind of data, known data. We call labeled data. This process we call supervised. So we we create a model, and this part we call training. So we train the code, the algorithm, they are apples. So you should learn those are apples. And after, if you test another apple without putting inside, and show the program or algorithm, is there's an apple, is it an apple or not? So it can easily predict under this model, and it gives it is an apple or not. So it easily classify this apple, is it apple or whether it is apple or not. And unsupervised learning, in unsupervised learning, you have many fruits like apple, banana, and peach. So without any kind of labeling, you just give the input data to the model, and model can try to cluster the shapes, the colors, and so on. And there is a clustering result. There are apples, there are peaches, and the bananas there. So. And also there is the, we know the classical machine learning things, we need features in advance. So we should know there is the car, there is the apple, and so on. So before doing a model, first we should characterize, we should analyze which kind of features for that input we need, the very crucial process for us. At the end, it classify, and it is whether it is a car or not, it gives as a classical machine learning algorithm like that. And if we consider deep learning, it is already inside the feature extraction. It's already inside, and it easily can say this is a car. It's the deep learning don't say like that. Deep learning doesn't say like that. It is a car or not. It is, there is a different shape is there. You should do at the end just like that. And if you give a label at the end in this way. Okay, machine learning. If we divide supervised and unsupervised, there are the classification and clustering parts like that, and there are many algorithms. You can see here. Those are coming from scikit-learn library, TensorFlow, Keras. All those are related with Python. You can find another programming architecture or MATLAB or something, Microsoft things. So you can find. I'm just giving a basic example for this part. So if you use a Python programming language, and then you should learn scikit-learn part. It is the library for those machine learning algorithms. And then you should learn maybe TensorFlow. Inside there are let's say array structural part, and your GPU or CPU can use those kind of TensorFlow libraries to run on that hardware part. So we need those kind of TensorFlow parts. And then maybe you can check the Kaggle website, some projects there ongoing. Maybe you can join, and you can visit the scikit-learn, and you can read the machine learning algorithms, how they run inside. So on the left side, the classification function, you can classify two classes as a probability on the point of view. And then there is the regression as a linear function. So you can maybe find the path as a linear function. And then there is the clustering part on the right side. If you cluster some points, but that you don't know which is meaningful. And then if you give a number, let's say the calming number, the algorithm will understand there are three different classes here, or clustering parts. So it means it can easily understand I have to divide three classes, something like that. And this is another process, another understanding for the clustering part. Okay, now I will give two examples. One is comparing 6 machine learning algorithms for galaxy classification. So these are just the supervised examples. And at the end, I will give a unsupervised machine learning example. Now we have 6 machine learning algorithms, and they are all supervised. And what we use as a data, we use SPSS Galaxy Zoo data, 60,900 galaxies. They are already labeled, they are already classified as ellipticals and spirals, as you see the numbers, visually classified galaxies. The redshift range in between 0 and 0.15, and they have Serzic indices, so it means they have the morphological definition as a number. We call Serzic index, let's say. And we train and test 70%, 30%. We train 70%, the numbers there, and 30% we test. And we will have results, I will show you. And we compare the same algorithm, what we use for Galaxy Zoo, SPSS galaxies, we use the same algorithm for our classification. We use CFHTLS Galaxy Legacy Survey data, 2,500 galaxies we visually classify, and you see the elliptical and spiral numbers as labeled, and the redshift between 0 and 0.5, and training and test as you see. So what we did, we have the data, I think my cursor, you see my cursor, the data, the Galaxy Zoo data, and our own zoo data. We visually classified the CFHTLS data. We use 6 machine learning algorithms. They are here on the left part. They are XGBoost, NaviBias, CNN, SVC, NN, and random forest. We just apply those algorithms to see if we use or let's say which parameters, which features for those data we should use, and what we get at the end. We do with 8 parameters, it's 8 feature of data, 8 feature of galaxies, like Serzic indices, effective radius, B divided by A, and so on, or the colors. And we have 4 photometric parameters, like colors indices, and we have 4 structural parameters, like Serzic. So at the end, we have the result. Okay. Let's first look to Galaxy Zoo data. If we run 6 machine learning algorithms, we have the 95% of accuracy for XGBoost algorithm. For random forest, 95, and so on. It goes like that. And if we see the confusion matrices, it is the prediction label and true label. The true label is the first, already in advance we gave the label, and the program predicts which galaxy is it, which type of galaxy is it, and this is the numbers. There is a good correlation or not, or as you see, the 95% is very high for the prediction. So the Galaxy Zoo data is like that, but this is for 8 parameters. So we have 8 different features for that those galaxies. If we do some structural parameters, 4 structural parameters, as you see in the second synthesis, with the same algorithm, we have a little bit lower accuracy, 93. And with the 4 photometric, not the structural, but photometric parameters, we have much more lower accuracy, getting much more lower accuracy. So at the end, with 8 parameters, it means more features, more accuracy at the end. So there is the receiver operating characteristic on the right part. As you see, false positive rate, true positive rate. The true positive rate is supposed to be 1. So when you go the left corner, it means it is the 8 parameters is the highest corner position. So we should do more with more parameters if we do that algorithm. And this feature selection importance, if we compare the impact of those 8 parameters, you can see here, for structural parameters is there the first CI is the best one for importancy, and if we for photometric features, the importance is the color indices, so UI, so 1.5, something like that. And if we use 8 parameters, the CI is also the both maybe XGBoost and the random forest, it is CI, something like that. If we apply the same algorithms to our visually classified data, so as you see, the number of our classified galaxies is low. It's 2,500 galaxies. So the accuracy is suddenly gets down low, because it was 95%. Now it's 87%. So our maybe a little bit low than if you compare with less efficiency from the less amount of data. And here for structural parameters, structural is very important to classify the galaxies, and photometric is much more less, as you see. So here is the 8 parameters is the top corner solution. So the importance here is the effective radius. As you see, the effective radius feature is the important one. So we can compare the 6 algorithms, like 6 ML algorithms give almost the same result with 8 parametric features. This is very important. The best accuracy scores obtained from those 2 machine learning algorithms, RF and XGBoost. And photometric parameters are less effective than structural parameters. Just this is our result. We can maybe, if your data is different, or if your features are different, maybe you will have another result. To select parametric features is crucial for the ML algorithms, and to increase the accuracy, it plays very important role. After certain redshift human, we know that, won't able to distinguish galaxies in between. So we should do those kind of application. We should need those kind of application, because if you go more deeper in the universe, so your images will be a little bit smaller. So your eyes maybe doesn't detect which galaxy is a problem. More classes of morphological types mean less accuracy performance. So if you just divided 2 sections, elliptical or spiral. So if you put another classes, maybe your accuracy will go down. So this is another problem you should consider. To extend visually, we need to extend visually classified samples and test the algorithm. So if we have more galaxies, it means you will have more accuracy. To choose a robust and effective parameters by using PCA or feature selection algorithms. So it's very crucial, because if your features is not good, it means your accuracy goes down. So you should define your features, and you should use some algorithms for defining the features is very crucial. And then it was the supervised. Those are the supervised example. And now I'm just going to try one unsupervised model, Gaussian mixing model. It is a model. All samples are generated from a mix of finite number of Gaussian distribution with unknown parameters. As you see, there are points, and this model do some Gaussian on the center for the density points, dense points. So on the right side, in the middle picture, there is a picture in the middle. This your point, and the program trying to find the Gaussian Gaussian fits on those data, and easily you can do a clustering like that. So you need a k-mean number to, as you see, the k-mean clustering part and hierarchical clustering part on the right corner. Those are the how we see the data, how we want to see the data. And this number goes to whatever you need. Before, in advance, you find the right number for k-means or for Gaussian mixing model or for clustering. Another problem. So very quick, how we can do those kind of applications. I used Anaconda. You can use Anaconda. There is Jupyter Notebook. This Jupyter Notebook, you can easily write the Python codes. You can run instantly. You can run immediately, see the results. It is just a simple and user-friendly interface for running those kind of programs on the computer. So I'm now stop sharing and sharing another thing, another, where was it? Just a second. Oh, here. Okay. Share. No, not this one. Oh. Now you can see my web browser, and inside that browser, Jupyter Notebook is running, and this is a GMM Gaussian mixing model. This code is written by Untitled Chapter. Today he has a talk in the student presentation section. And now we have 5,319 galaxies in a data, CSV data. They are just galaxies coming from CFH3, I guess, and they have array deck. So we know the positions on the sky, and we have the VPOT, so photometric redshift of those galaxies. So we have three dimensions. One is array, one is deck, and one is the distance from us. It's the photometrically determined distance. So we can use what we are going to do. We are going to do a three-dimensional or clustering, not three-dimensional, but considering all three dimensions, and to if there is a cluster of those galaxies at the end. Just give a quick sense, or just give a sense to how we do that. If you wanna, maybe you already use those kind of things. If you don't, you can see we just import for Python some libraries, and then there's the scikit-learn here, scikit-learn mixture. It's very easy to import those kind of libraries inside the Python. Import the Gaussian mixture model, and then we have the data, we have the three dimensions here, and we trying to calculate the commons, and those are not important because I can't explain everything in a very short amount of time. So just give a sense to see how we can do that. You can find those kind of things in the math, and you can easily read, you can easily dive on those kind of problems, and you can use for your data. And at the end, we have this. This is a clustering in 3D, let's say, but not 3D, but we can say it is a clustering. How in front of array deck, there are some density points. So the galaxies are together there. So it means we can easily cluster those kind of galaxies with those three. It is very quick, not maybe scientifically reasonable thing, but okay, you can do in this way. So it is a projected distance. So at the end, maybe you can create some 3D mapping like that. People do those kind of. So this gives a quick sense for those kind of things. Okay, now I'm finishing. Thank you very much for your attention. If you have a question, I'm trying to answer your question. Thank you. Okay, I think there is no question. We can give a long. There is Oscar. Okay, Professor Oscar, please. Your hand is up, but we can't hear you. Okay. Thank you. No, we can't hear you still. Your mic is on, we see. You can write as well. And after break, we will.
There's a question, Korhan, in the Q&A.
In the Q&A, okay. Let's check. Yes, you can run without Anaconda. Just use the web browser. It needs web browser. Mine don't say. Okay, Oscar, don't worry about that. Later we can discuss about your question. And we will meet again. Let's say this 9:30 UTC time. 9:30. So we will have a 1 hour break. Thank you very much again. Your question concern distributed computing. Yes. Okay, we can discuss later. Thank you. See you then. Bye-bye.